saw the corrected version of it. What's the airflow through a duct of 12 inches by 12 inches with a velocity of 1,000 feet per minute? The Q is equal to V times A, right? So A is 1 square foot, right? 12 inches by 12 inches. Some of you decided to multiply 12 times 12 to get square inches and then convert it into a foot. I'm not sure why you bothered with that. But yeah, it's 12 foot by foot, 1 square foot, 1,000 feet per minute. 1,000 feet per minute times 1 foot squared is 1,000 cubic feet per minute. Okay, now, of course, some of you guys, the right answer wasn't there, of course, so you just highlighted it and stuff like that, wrote it in, which is fine. 2-inch by 5-foot slot hood exhausts air at the rate of 2,000 feet per minute. How many pounds of air are exhausted per hour by this hood? Now, why is the weight of the air relevant? Well, weight has the amount of air that we're moving in cubic feet. If you change that to weight, primarily since we're working on the surface of the earth, you're talking about mass. So we're talking about moving a mass of air at a certain velocity, which is work. So it helps us to understand this because later on, when we have to figure out how many horsepower of fan we need to know how much stuff we're moving at what rate. Okay, so let's do that. 2-inch by 5 foot. How many square foot is 2-inch by 5 foot? Let's see. 5 foot is 60 inches, right? 2 times 60 inches, rather, 2 times 60 inches, 120 inches, right? So what fraction of a square foot is that, right? Divided by 144, as you guys did for the other problem unnecessarily, I thought, but, right? 2 times 60 inches. Slide is 120 inches. It's 120 square inches, right? And I'm going to divide 120 by 144. So it's 0.833 square feet, right? So we have our area, right? So what else do we need here? We want to know the quantity of air that we're moving. It's moving at the rate of 2,000 feet per minute. So V times A is going to give us our Q. I'm going to go back to the calculator. Times 2,000 feet per minute is equal to 1,666.66 cubic feet per minute that we're moving through that slot hood. Now, we said we wanted to know the weight of air per hour, so I'm going to multiply it by 60. And it's going to be equal to 100,000 cubic feet of air. How much at standard temperature pressure? What does how much does a cubic foot of air weigh? Times? Maybe you remember? It's one of those constants that's going to come up quite a bit. I think I might have even given it to you there. Did I give it to you there? Right? It's bingo, 0.075 pounds per cubic foot, and that's equal to 7,500 pounds of air. Okay, and I think that was actually one of the choices. Well, I lucked out this time.
How do we get 100? What was the 100,000?
Okay, I'll back up. Okay, so first we figured out what the area was. It was roughly 0.83 square feet, right? That's the slot. Yeah. We said that air is moving through that slot at the rate of 2,000 feet per minute. Right. So I multiplied that by 2,000 feet per minute, and this gives us the cubic feet of air per minute that we're moving. Right. I multiplied that by 60 to get the cubic feet of air per hour, right? It really came out to 100,000 because it wasn't exactly, right, 100,000. And that I multiplied by 0.075, right, to convert from cubic feet into pounds of air. So that's the number of pounds of air per hour that we're moving through that slot. Okay, and again, you know, in English units, we very frequently exchange casually pounds for mass. We know pounds is not really mass, but since we're working at STP, we can use it basically interchangeably. Okay, so, okay, good. So take a look at the next question. If I can find it. It's a Word document. Let me find it. Here we go. Okay, number 3. And I'm going through this for a point because we're going to graduate from this very quickly. At a point, at an upstream point from a fan, upstream, think about this, upstream, you're upstream, which means the water is flowing past you to the fan. So you're on the suction side of the fan. If you're downstream of the fan, you are on the pressure side of the fan. Make sense? Okay, so we're upstream. So think about it like if you're a hunter, right? You want to stay downstream because you don't want the animal to smell you or something like that. Okay, so at the point upstream from a fan, negative pressure, velocity pressure is equal to 3, and static pressure is equal to 3.5 inches. What's the total pressure at the same point? Okay, well, it's going to be velocity pressure plus the static pressure, which in this case is negative, right? So that's going to be minus 1/2 inch. Okay, a little tricky because I didn't give you the sign. I made you deduce what the sign had to be since you were upstream of the fan. Fill in the blanks for the pressure inches at the relocation. The duct size is 1 foot by 1 foot and does not change. Why is it relevant that it doesn't change? Why is it relevant that it doesn't change? If the velocity pressure stays the same throughout, right? Because the only reason same quantity of air is coming in is going out, so the velocity of air going through there is never changing, right? So the velocity pressure is going to be 1.5. B and D are going to be 1.5, right? So you should be able, since the only thing that's missing here is the total pressure here and here, you should be able to just subtract, add to velocity pressure and static pressure. This is minus 1.5. This is going to be 1.5. It's going to be minus 1.3. This is going to be 1.5. Whatever adds up to a negative 1.0 from 1.5, which is, I guess, 2.6, right? 2.4, 2.6. So you can deduce that just using total pressure is equal to velocity pressure plus static pressure. Everybody comfortable with that? Right? Yes? What is the average velocity of air in a duct where the velocity pressure is equal to 1.2 inches WG water gauge, inches of water, basically? Okay? So how would you approach that? Right? Velocity of air. The only thing you need to know here is the velocity pressure to deduce the velocity, because that's the only thing that impacts the velocity pressure. The total pressure, you need to know static pressure also, but the velocity pressure is just the force of the air, the moving air. Okay, so there's a couple of ways we could do that. We could use a formula, right? We have a formula that relates velocity pressure, square root, and 4005. Remember that formula?
Right.
Even easier, you could go to the chart.
Right. Is it fine if we go to the chart? Because who wants to?
Absolutely, positively. Don't bother if you have a chart for it. Don't bother using the equation because you'll just get just another reason to get it wrong, right? If you inadvertently reverse some of the variables and so on. So we could use a couple of charts. Chart 5, right, has that. In fact, I have the charts here. Let me find it. Where is the charts? Chart 5. Let me alphabetize these. Here, chart 5 is the nomograph. And what did I say the velocity pressure was? I hit it. 1.2. So 1.2 looks like it's roughly, velocity pressure is 1.2, roughly about 4,200 feet per minute, right? And actually, I think chart 7 is a little bit more accurate. If I look for chart 7, velocity pressure to VP conversions, velocity pressure 1.2 is 4,385 feet per minute. Okay, and if you want to use meters per second, you have that also, or millimeters instead of water gauge instead of inches water gauge. You have that also if you need to. But again, we're going to work mostly in English units. Okay, next. What is the flow rate through the above duct if its dimensions are 12 inches by 18 inches? Okay? So Q is equal to VA. We know what V is now, right? What's A? Well, that's a foot by a foot and a half. And it's a rectangular duct, so it's going to be 1.5 square feet. So Q is equal to 1.5 times the velocity. And what does that come out? It probably comes out to roughly like 6,000 or 7,000, right? Cubic feet per minute. If you actually write this out more carefully, you can do dimensional analysis to make sure you're not screwing anything up. So make sure that your dimensions come out feet times feet squared times feet per minute is cubic feet per minute. Okay, 7. What is the 90-degree elbow loss factor, K elbow, where the elbow radius of a curvature is radius to diameter is 2. The radius is 2 times what the diameter is in a smooth transition elbow. That would be like PVC or something like that. So what chart will we need for that? Let's look it up. Chart 13, elbow loss factors. And smooth transition, that means it's something, a very smooth pipe. It's not one of these jointed sections, and it's not an abrupt miter, like right turn angle and so on and so forth. So it's a smooth transition. It's 90 degrees. And we said the R to D ratio is 2.0. So the K factor is 0.13. What if I told you it was a 45-degree angle? What would the K factor be instead of 90? Right, it just turned that way, huh? Exactly, it's half of the K factor for, and these are all approximations. Of course, you have some descriptions of how to do this down here as well.
Just one question.
Sure.
When it says like in my mind, the radius will always be half of the diameter.
Oh no, hang on a second. They're talking about the radius of the turn.
Oh.
So, like in other words, if the duct is 12 inches in diameter, and in this case, if the duct is 12 inches in diameter, the radius of the turn would be 24 inches, twice that.
Oh.
So the radius is twice the diameter. So if the radius of the turn were 1 foot and the duct diameter is 1 foot, that would be an R/D of 1. Right? So it's the radius of the turn. In other words, is it a tight turn or a gradual turn? Right? The radius of the turn over the diameter of the ductwork. Okay, so that's your transition radius. Okay, so that's going to be point since it's 90 degree instead of the 45 degree I suggested just now, it's 0.13. What is the actual static pressure loss in inches? You're losing energy when you make a turn because it's hitting the side of the duct. There's vibration, there's heat generated, and so on. What's the actual static pressure loss in inches of water of the air flowing through a 90-degree smooth elbow, what we just had, at an average velocity? V is equal to 4,650 feet per minute. R over D equals 1.5, not 2, but 1.5, so tighter turn. Assume standard pressure and temperature. It's still a smooth elbow, and D is equal to 1. What's D? That's the density factor. So, we've been assuming that anyway. So what do we need here? We need to figure out what K is, because the loss is equal to the velocity pressure times K times the density factor, which is equal to 1. So what we know the velocity is this. We have to convert that into a velocity pressure. Now, I'm going to call it 1.2 because then we just do an example that's almost exactly that number. Right? It's close enough, right? So let's say the velocity pressure, going back to our charts, is 1.2 inches of water, right? The R over D is 1.5. Let's go back here. 1.5 of smooth transition is 0.15. So the loss is going to be 0.15 times 1.2. So you lost 0.2 of a little less than 0.2 of an inch of static pressure going through that turn. That means you have to suck that much harder, 0.2 of an inch of water harder, to make up for that turn, so you maintain the velocity that you want going through this ductwork. Okay, because that's really what we're after. We want to know how much of this energy we're going to lose to this ductwork and the turns and so on. Okay, what's the actual static pressure loss in inches of air flowing through a 45-degree smooth elbow at an average velocity of the same thing, except this one's 45 degrees. I know already it's going to be, K is going to be half of what it was before, so it's going to be half what I just said. Instead of 0.18, it's going to be 0.09 inches of water loss. Okay, everybody okay with that? Right. The only difference there was it was a 45-degree turn instead of a 90-degree turn. Same velocity, same kind of elbow, same kind of pipe, smooth pipe. Right. So VP times K. Right. VP is the same. K is half of what it was before. So instead of being 0.18 like it was before, now it's 0.09. Right. Because K is half.
So the loss is also half.
Right, exact. That's the loss. Exact. 0.09 is the loss.
So can we generally assume that?
Put a 45 degree.
Yeah, when the angle is half, the loss will
Yes.
be.
Yep. It's proportional to the end.
Right,
Yeah.
exactly.
Using those charts. Is it really? It's much, if you really use fluid mechanics to really calculate it, my guess would be it'd be much more complicated than this. But this is good enough for us to use to do an initial design on ductwork.
So that would be my other question. In real life, do
Yeah.
you use the charts or what do you do?
Use the charts. In real life, you would use the
So it
charts.
works.
Absolutely, positively. Yep. Okay. And in fact, in real life, we're going to find out the way this guy does it, the guy who wrote the book, designs exhaust systems professionally. He has his charts built into spreadsheets. So instead of doing this calculation, he would put, oh, I got 3 turns, 3 elbows. They're all smooth turn transitions. One's 45, one's 90, and so on and so forth. And it would calculate, and it would calculate it would do a calculate, put in the areas, the size of the ductwork he's using, and it would do the calculations for him. But we're going to get to that point actually eventually. Okay, what is the friction loss and friction loss K factor for a galvanized iron duct with the following parameters? The diameter is 5 inches. The average velocity, right, is the average velocity is really what we're interested in. We may not say average every time, but we really mean the average velocity in the duct. The average velocity is equal to 4,000 feet per minute, standard temperature and pressure. So how much loss do we have per foot for a galvanized iron duct that's 5 inches in diameter at that velocity? Well, again, the static pressure loss is going to be equal to the K value for that size pipe and times the velocity pressure, that kind of pipe at the velocity pressure. So why do we need the diameter? Well, we need the diameter because, well, we know the average. Well, let's take a look at this. We don't need the diameter, do we? Well, because we got the velocity, and we're going to have K, right? What's that? If the diameter were different, the velocity would be different. So the diameter is really extraneous information here. What's that? For the K value. Let's get the K value right now. Okay, so let's go to a chart. There's a couple of ways I could do this. I think chart 5, right? Okay, so chart 5, we have the velocity is how much? Did I have the velocity or velocity pressure?
Velocity is 4,000.
For the velocity is 4,000. Right, here's the velocity is 4,000. And so the velocity pressure, velocity is 4,000.
The velocity is 4,000 and the diameter is 5 inches.
Yeah, oh, actually, I am going to need the diameter. Hang on a second here. Okay, so air moving, actually, think about it. When you think about it, air moving through a 6-inch duct is in more contact with this. There's a higher contact by percentage in a small duct than there is in a big duct with the area of the surface of the duct, right? So there is a difference, right? Okay, so let's calculate this. I'm gonna put a line through here. Okay, so 6-inch duct. Here we go. 5-inch duct. 5-inch duct at 4,000 feet per minute. Okay, so what's the K value there? Yeah, it looks like 0.05. So every foot of this ductwork that you have, you're going to lose that much static pressure. So if you have 100 feet of this ductwork, how much static pressure are you going to lose? 0.05 K times 100 feet, right? Times the density factor, which we're leaving at 1. So you're going to lose half an inch of static pressure. Okay, so let's see. 0.05. Actually, you're going to lose more than that. You're going to lose 5 inches. 0.05 times, right? Because that's a lot of velocity for that small duct. 4,000 feet. 0.05 per foot. Okay, yep. So next, okay, let's see what else we got here. What is the friction loss for a length of galvanized iron duct with the following parameters? The diameter is equal to 8 inches. Q is equal to 1,000 cubic feet per minute. Did I get velocity? I did get velocity there. And the length is equal to 43 feet. So we have 8-inch diameter, 1,000 feet. Q is equal to 1,000 feet per minute. Well, do I have Q here? Let's see. The volume flow rate, I have that here as well. So the volume flow rate is 1,000 feet, 1,000 cubic feet per minute. And I have the diameter is 8 inches. Oops. The diameter is 8 inches. So my K factor is 0.03. And how many feet do I have? 43. So it's 43 times 0.03. Okay, that's going to be my static pressure loss. Okay, and notice that as the ductwork gets larger, what happens to the K value? What happens to the K value if the ductwork gets bigger? Goes down, right? Because you have the same velocity of it, you have the same quantity of air going, but it's going much slower, and it's also there's less of it in contact with the side, even with the velocity staying the same, right? As you reduce the size of the ductwork, right? Whoops. Let me get that to 4,000 again. As you reduce the size of the ductwork, right, the K factor goes up. As you increase the size of the ductwork, even with the same velocity, you're also going to get a smaller K value as well, right? Because there's less, in a circle, right? You have this big a circle, you have this smaller circle, a lot more of the air is in contact with the side and being affected by friction. Okay, so that was the last one, I think. Okay, so we got kind of a start on this now. Okay, so I think that was the last question, if I'm not mistaken. Did I close this? Yeah, okay, good. So now let's go. I have a PowerPoint here. I don't even know if I made this available on Blackboard. I put it there, but I didn't turn it on, I don't think. That's okay. We're going to go through some examples here.
You said that we can correct you're going to grade it and then we can correct
it. Yeah, you can redo it. Yes, absolutely. I'm more interested in the fact that you get it done right in the end, than you get it done right the first time. Yeah, you can. I'll give you another week to do it. Okay, so let's see.
Do we have exams in this? How do we do it?
You're going to have the tables, right? You can either bring your own tables, or I will tell you in advance on which tables you'll need. I'm not going to print out 87 sets of tables. I don't think. What I may do is, I may get them to give us computers so that we can put the tables on the computers. You know what I'm saying? We have laptops. They'll let us borrow laptops. You can bring your own computer, or you can use a borrowed laptop, and I'll make sure that they have the charts that you'll need on there. Okay? Make sense? Right? Rather than print all this stuff out. It's going to be kind of complicated. I could do that too. I might. I'm not adverse to that. I would like to have part of it in here. Keep you honest, because just so I can gauge, if this stuff is getting across. Okay. Let's talk about this. This is some of the formulas that we went over before. Coefficient of entry is kind of like, as far as I'm concerned, a throwaway. It's basically the efficiency of the hood. The real thing I'm interested in is the hood entry loss. How much suction do you have to have, and how much energy do you lose pulling air through that hood? Because the hood entry loss tells me what the static pressure of the hood has to be at the point where you connect the ductwork to it. That's where it tells me what I need to produce with the fan, right, in order for this hood to work the way I want it to. The coefficient of entry is really an efficiency measurement, right? It's equal to the velocity pressure divided by the positive value of the static pressure. Let's think about this. if the velocity pressure is equal to the static pressure, right? That means that the velocity pressure and the static pressure are the same. It's basically, that means that there's no resistance. 1/1, the square root of that is 1. It's 100%, 100% efficient, right? So the more velocity that you have and the lower the static pressure is, right? That's that's a bigger number than if the static pressure were high and the velocity pressure was small, right? So if you have to suck real hard to get very little velocity or velocity pressure, that's a less efficient hood, and that number is going to be, when you take the square root of that fraction, is going to be a smaller number. So it's really just the efficiency of the duct. Nice to know, but not something that you're going to use probably in your design. You may want to use it to compare different hood designs and stuff like that, but we'll see how we might apply that. Okay, we talked about different kinds of hoods, slide hoods, planet hoods. These equations, the Delaval equations, the chart, was it chart 11 or chart 11, where we have all the hood equations. We started to talk about that, talk about static losses. We talked about the other kinds of hood, the kind of hood where you supply air, you blow air across the table and you suck it in the other side. Here they're just mentioning that in push-pull design, you have to balance it. You have the same amount of air going across as you're pulling away. Otherwise, you're blowing air too fast and you're defeating the purpose of the suction on the other side. Balancing of these systems is supply air. We talked a little bit about portable hoods, like the asbestos ones we use in the lab. Mentioned, baffles and turning vanes came up. Hood static pressure, which is kind of the key number that we're really interested in. Okay, so a sudden expansion of air. Did we talk about that vena cava thing? The idea that there's certain system effects, like when you suck air in, where you get this area of very high turbulence, where the air is kind of compressed and then expands suddenly. We got to stay away from areas where there's these kind of system effects, because we need to be far enough away from those kinds of things to get accurate measurements of the duct velocity pressure and static pressure. In general, depending on what kind of connection it is, what you're connecting to, that's usually 2 to 6 diameters away from the device, the fan or the hood or whatever. That's duct diameter. In other words, 12-inch duct, that would be 2 to 6 feet downstream from the duct. Okay.
Is that an English term? Vena contractor?
Well, it's Latin. Latin. Yeah. Vena cava. I guess that's like collapsing vein or something like that.
And I think
empty vein. Yeah.
And vena cava is one of the big veins in the body.
Yeah. Yeah. Okay. Sudden expansion of side panel. We talked about how side panels and enclosures can help make the hood more efficient and more effective at capturing contaminants. Talked about the hood in itself imparts losses. We talked about capture velocity, how fast it has to be moving at the distance where you're working with the contaminant, how fast it has to be moving in order to capture that contaminant. And it's not mentioned here, but we also brought up the idea of transport velocity. Once that contaminant is captured and pulled into the hood and into the ductwork, you got to make sure the air is moving through the ductwork fast enough to keep it from settling out in the ductwork as well. That's transport velocity. We're going to be looking at that as we build our hoods. Portable fuel hoods, area, and we talked about areas and stuff like that. Big deal. Okay, there we go. And this is, kind of like a typical system. Hood, duct, filter, some kind of air cleaner, more duct, and the fan. We're looking at everything for this week. We're only concerned with everything up to the fan. We're going to make believe that the fan is free discharge. There's no resistance to air coming out of the fan right now. That's not true. There will be resistance because you have to have ductwork coming out of the fan. It might have to make a turn, go up to the roof, discharge outside. So there's going to be resistance to flow that's added by the discharge from the fan as well. But for right now, we're just designing the suction side of this thing, which is probably 80% of the actual system. Anyway, okay, and this is where that's where we're going to measure our static pressure for the hood. We're going to use what we know about this hood, the equations, the manufacturer's information, and we want to determine What does the static pressure, how much suction do you need right at that point? Static pressure hood, what do you need at that point to deliver the amount of airflow from that hood, the capture velocity that you want to protect the worker? Okay, and the static pressure, what is that determined by? That's determined by how much you lose, how much static pressure you lose by sucking air into the hood, right? That loss is called the hood entry loss, HE. Okay, we got a formula for that. The static pressure, positive value of static pressure is equal to the velocity pressure plus the hood entry loss. If this is in a perfect world, the static pressure and the velocity pressure would be the same. Remember that formula? Coefficient of energy, VP, the square root of VP over positive value of static pressure would be the same. So the minute you have resistance to flow as you're trying to suck air through this hood, you have a loss. That loss is called the hood entry loss, HE. And that's equal to the velocity pressure, the static pressure that we need is the velocity pressure that we desire, the velocity of air that we want there, plus making up for the losses that we have entering that hood and getting to that point. Okay. Static pressure loss is going to be equal to, again, we got a factor. That factor, K, is determined by the manufacturer of the hood. They tell us that based on their design, this is what you should anticipate as a loss factor for this hood. What's it equal to, that static pressure loss? It's equal to a K factor from the manufacturer times the velocity pressure. Again, the faster you're sucking air, the more that resistance you're going to get. So that's part of the whole equation. And that's really the only loss that you have at the hood entry is. So it's the static pressure loss is basically the same as the hood entry loss. Okay, makes sense? Okay, good. Okay, and here's our formulas. The average velocity in a duct serving a hood is 2,000 feet per minute. The loss factor for the hood has been determined to be 2.2. That's K factor for that hood, 2.2. What are HE and the static head pressure? Okay, well, what do I need to know to calculate that? I need to know the velocity pressure, right? And I need to know the hood entry loss. So what's the velocity pressure in this hood if it's 200, what's the velocity pressure if the velocity is 2,000 feet per minute? Somebody convert it? You got the table or the formula? Right. I don't want to drop out of PowerPoint if I can avoid it. Somebody got the velocity pressure? Right? Chart. 0.25. Okay, so the velocity pressure is 0.25. The loss factor for the hood has been determined from the manufacturer to be 2.2. So the static pressure loss, the hood entry loss, is equal to 2.2 times 0.25. What's that come out to? That comes out to 0.55. What happened?
You wrote up there.
What? I'm sorry, what happened?
No, you wrote everything up.
Oh, all right. Yeah. Okay. Yeah. Okay. Okay. So the hood entry loss. Oh, it's there. Oh, crap. Okay. The 2.2 times 0.25 is 0.55. No wonder you got the answer so quick. Okay. That's your hood entry loss. What's your static pressure for the hood? What do you need at that point on the hood? It's equal to our velocity pressure plus what we have to make up for the loss. What was our velocity pressure? 0.25 inches. Our static pressure, head entry loss is 0.55. Add them together, and 0.8, right, is going to be the static pressure at the hood, at the back of the hood that we need to make this thing work for us. Okay. Okay. Let me see if I click back here. Oh, here we go. Okay, hood entry loss. You could actually use the formula if you want. V is equal to the square root of velocity pressure. To calculate it if you didn't have the table. We get the same answer. Okay, and 0.8, a negative point, again, now keeping in mind it's negative pressure, static pressure. Okay, average velocity in duct serving a hood is 2,000 feet per minute. Loss factor from the hood has been determined from the manufacturer to be 1.5. What's the hood entry loss? And what's the static pressure, the hood static pressure? Okay, what's the hood entry loss for start? What's velocity pressure, number one? Same, right? What was it? 0.25?
0.37.
Okay, 0.375 is what our hood entry loss is. Our velocity pressure added to our hood entry loss is how much now? 0.375 plus, what was it again? 0.25, right? Okay, so, yeah, okay, so 0.25 plus 0.375. Point, 0.625, I think.
Yeah.
Right, inches, negative 0.625 inches of that's our static head pressure. Okay, now again, the efficiency is just those two numbers divided together. Okay, and I wouldn't worry about that second formula. You probably never run into it again. Okay, hood entry loss for a bell mouth hood, duct velocity equals 3,000 feet per minute. I didn't give you K. What are you going to do for K? I'm going to have to drop out of this, I can see. What are you going to have to do for K? You got to go to your tables, right? A bell mouth hood. Oh, bell mouth hood. Okay. Let's see. Bell mouth hood. What's the K factor for a bell mouth hood? 0.04. Okay. So we get that from our chart. We go back and restart PowerPoint, I guess. 0.04. Right? 0.04 is our K factor. Our duct velocity is 3,000. What is our velocity pressure? Right? What's that? Okay, 0.5. Okay. Okay. Velocity pressure is 0.5 times K is 0.04. Right? So what does it come out to? 0.2. 0.5 times 0.04 is 0.02. Right? So our 0.5 times 0.04 is very little loss with a bell hood. 0.02, right? Am I right?
Mm-hmm.
Okay, 0.02, right, is going to be our head entry loss. But, okay, 0.52, this 0.02 is going to be our hood entry loss. What is our static pressure for the hood going to be, though? It's equal to our velocity pressure plus our hood entry loss, so it's going to be 0.54. Okay, that's what we need to make that work. Hood entry loss for a plain duct. Hood duct velocity is 3750. Okay, got to go back again, right? Now you do it. I'll see if I can't give you the. I'll give you a plain. There you go, plain duct end. The K factor is 0.93. What a difference, right? 0.93 versus for the bell entry 0.04. Right, big difference, right? And so the design on these things makes a big difference. Okay, so what? So you guys want to calculate that? Okay, what are you going to calculate first? Velocity is 3750. What do you need? You need to convert that to velocity pressure, right? Now you could use the formula. Don't remember, V is equal to, right? V is equal to 4,005 times the square root of VP, right? You could do that, you know, if you got your phone or a calculator handy, right? You could use the formulas if you need to. Okay, so what's the velocity pressure? 0.88 is the velocity pressure. Oh, are you giving me the whole static pressure?
No.
Now 4,000 feet per minute. Did we count? Wasn't it like 0.5 before? Something like that. I forget.
3,000 was 0.5. How much? This is 37.
One. What? Why is it 0.9? Isn't it 0.5 and 1 the same?
It's 3,750.
Oh,
It's
okay.
So he's not.
So he's
4,000 feet per
0.88.
4.88. Is that what it is? 4,000. No, I get something different. 4,000 feet per minute. I get one. Get 1 inch.
it 370?
It's a little less.
Three.
Oh, there's 37, I'm sorry, it's 3750, right? 3750. Yeah, 0.88 is close enough. Okay, so 0.88. 0.88, right? Okay. I thought you guys were supposed to be doing this. I mean,
0.81.
0.8,
No,
0.88, pretty close.
No, the answer.
Oh, okay, well, you're getting ahead of us here.
Yeah.
Okay, so K, 0.88, right?
It's 0.93.
Times the velocity, times K, which was what, 0.993? So what is that?
0.813.
0.818. Okay, we got to add that to the velocity pressure. So it's 0.88 plus 0.81 gives you your negative static head pressure. So you need a static head pressure of 1.6 roughly to account for the static pressure of 0.81 loss that you have and for the velocity of pressure of 0.88. That's the whole idea here. The static pressure has to be high enough to account for the velocity pressure that you've created and for the loss that you had going into the hood. Okay, a side draft hood with baffles exhausts with room air temperature acid solution. We want to maintain a capture velocity at the edge of the tank of 125 feet per minute. What volume flow rate would you suggest? So we got to find a side draft hood. Okay, let's go into number 11 and see if we can't find that kind of hood. Side draft hood. Let's scroll through here. Oh, here we go. Side draft slotted hood with sides and back. Okay, TTO and STO. What do you think that stands for? Right? Let's look down here. Tapered takeoff duct or straight takeoff duct. In other words, the duct on the back of this, does it take the back and does it go off the slot and it's tapered, or just go right into a duct in the back, like kind of like a square duct or a round duct, right? Let's assume that it's a tapered duct, okay, and it's equal to. In fact, in this case, it really doesn't make much difference. Oh, I'm sorry, it doesn't seem to make much difference here. The K factor for this is 1.78. But wait a second, it's more complicated than that, isn't it? Right? Because we have to figure out, let's see, what velocity of air, how much air do we need to pull in order to have 125 feet per minute at the edge of this thing? Well, let's go back and look at this chart. Okay, the slot velocity, let's see, the quantity of air that you need to move is equal to the capture velocity times the length times the width times pi times 0.05. So what's our capture velocity? But they just tell us that they have to have 125 feet per minute, right? So it's 125 feet per minute times the length times the width. Did I give you the length and the width? What volume flow rate would you suggest? So the volume flow rate I'm going to open up my calculator because I'm not going to depend on you guys because I'm going to be here all night. Okay, so all right, so you can follow me on this. So it's 0.05 times the width. Let's decide what the width and length of this thing is going to be. Let me see if I don't have that on a subsequent slide. Did I give it to you on a subsequent slide? Volume flow rate. Okay.
I think on that slide itself,
I'm sorry, what's that?
in the picture,
it has the. I'm sorry, it has the length and width in there, doesn't it? Yeah, I did. I thought I must have given it. I just couldn't see it from here on this little screen. Okay, it's 1.5 foot by 6 foot. Let me get back here. Okay, so I'm going to clear this again. So it is 0.5 times 125 feet per minute times 1.5 feet wide times wide times, what was it again? 6 feet wide equals times, did I times it by pi yet? No. Times 3.14 equals 1,766 cubic feet per minute. So what did we just discover? We just discovered that if you connect the duct to this and pull 1,766 feet per minute, cubic feet per minute of air across this hood, you will have 125 feet per minute on the table surface there to pull the contaminant away from the worker. Right? We found how much air we need to get that capture velocity that we want. Now that we know that, we can go back here and we can say to ourselves, okay, we need to move that much air, 1766. Okay, so now let's see what the next deal here is. Determine the static, I guess I left it at that, right? I could have asked you to do some other calculations based on that, but as it happens, I left it at that for this particular hood. Next hood. Determine the static head pressure required for a flanged hood providing a capture velocity of 100 feet per minute, 1.5 feet from the face of a 1x2 foot hood. So this flanged hood, it's like just a rectangular duct with a flange around it to keep the air getting pulled in from the side. Okay, notice the K value is much better than just a plain duct end, right? Not a lot better, but at least somewhat better. Okay, so that's the K value. So what's the static head pressure that you need in order to get a capture velocity of 100 feet per minute, 1.5 feet from the front of this hood? So that X, that length that you see there is going to be how far away that we have to be. Okay, so let's use this equation at the bottom. Here actually we calculated it. Calculate the velocity in the duct, velocity, pressure, and so on. Okay, so let me go back here. Okay, so X is the distance that we're going to be working, which is 1.5 feet, right? The area is going to be, what's the size of 1.5 feet? 1x2 is going to be 2 square feet. So it's going to be 0.75 times 10 times 1.5 squared plus the area, which is 2, times the capture velocity, which is 100 feet per minute. That will give you Q, how much air you have to suck to get that velocity, that distance from the front of that duct. Once you have Q, if you know the dimensions of the duct, you know what the velocity is, you know what the VP is. Once you know what VP is, you can then look up what K is, multiply VP times K to get the hood entry loss. And you can figure out what the static hood pressure has to be behind that hood, two diameters, 2 feet, several feet down from that hood in order to generate that velocity that you need. Okay, so again, we're calculating static hood pressure. Okay, now why am I beating this to death? I'm beating this to death because this is really the most important part of this calculation. I'm going to go back, we're going to run through these real quick, and then we'll actually do a nice, interesting exercise. I think it's an interesting exercise anyway. Okay. So if you read through the textbook, through the workbook, they're going to talk about the criteria that you should consider when you design ductwork. Among them is, and this would seem obvious, that it should last, the ductwork and the system you're building should last the life of the system, because you don't want it to break down and if it's not, because it's presumably protecting workers. Minimize maintenance issues. You don't want crap building up inside of it, so you want to make sure the transfer velocity is good. If you have issues where you think you might have some debris building up, you want to put clean outs there, so on and so forth. Provide consistent transfer velocity over the life of the system. In other words, if you put filters in, make sure there's a maintenance program to change the filters so they don't interfere with the flow, so on and so forth. And then they go into various transport velocities, which makes sense. For dust, you probably want 4,000 feet per minute. Okay, it really kind of depends on the size of the particles and the mass of the particles, but they're giving you a general range of 3,000 to 5,000 feet per minute, which you can kind of play around with depending on how big you think the particles are going to be. I'm going to be talking about an example, which might be a jeweler's table where they're using rouge to polish jewelry or something like that. It's a very fine dust, so you probably 3,000 feet per minute probably be more than enough. If you're doing a grinding operation where big particles produced, you might want to be on the higher end of that, like 5,000. vapors, right? Just gases that are not heated or something like that. They're just gases. They'll move with the air. Probably 1,800 to 2,000 feet per minute is likely to be optimal. Okay, scrubbing velocities for dry particles around ducts. You don't want coarse particles to damage system components and so on. So you may want to limit some of the velocities in some cases. Duct losses, we were talking about different kinds of ductwork. Roughness will determine. We stuck with a roughness of one when we talked about ductwork, right? And we're going to continue tonight to talk about a roughness of 1, which is typical galvanized iron ductwork. If we're using a rougher duct, coarser duct, if we're using flex duct, that roughness factor is going to come into our equation. We're going to have to adjust our losses for something that's not a nice smooth surface inside the ductwork because it's going to create more resistance. Yeah.
Just a minute. It says friction loss equals K isn't K friction loss? Is it friction loss equals friction loss?
K is a unitless factor. K is unitless.
It's a friction loss value.
Factor.
It's a friction loss factor.
Yeah, it's unitless, has no units, right? It's really kind of a percentage. You can kind of look at it as a percentage of loss. Okay, okay.
Friction loss, like write it out, friction loss?
Well, you'd probably identify what it's for. So for instance, elbow loss, you'd say it's the friction loss. It's loss to friction. All of these are losses to friction, right? So what you're losing in an elbow in static pressure is a friction loss. What you're losing through a length of ductwork is a friction loss. We probably will phrase them in terms of the source of the loss, like duct loss or elbow loss or hood entry loss and so on.
So friction loss is pressure unit.
It's inches of water, which is pressure. Okay. Exactly, or millimeters of water.
Whereas K is unitless.
Correct, absolutely correct. R is unitless also. R is a factor that you put in there for the roughness of the ductwork. Right? Here's the R, for instance. We're using 1, right? So if we're concrete, there are concrete ducts, by the way. There are concrete or masonry ducts that you will come across occasionally. That's much rougher surface. The R factor is 1.5, right? So in other words, what that's saying is you should multiply your K factor by 1.5 because now it's going to introduce a bigger loss. Corrugated flex duct is terrible stuff. Yes?
Hey, Professor, I got to leave.
That's okay.
My train messed up, so
that's not a problem.
I didn't reach up to like 12:30 last night.
I'm recording this, so if you wanna see what we did later on, what's?
Yeah, let's see. Last night there was no train going through. Got to take a cab.
Take a cab. You know, I knew this old guy for many years that grew up in this neighborhood. I think I told you this. Grew up in like East Harlem here, and as a little kid, he used to hang around. His family was kind of like wise guys, and he grew up like on 116th Street, First Avenue. It was an old Italian wise guy neighborhood, and he told me that he had a million stories. One of the stories was like when he was 6 years old, they'd send him with a paper bag to the police precinct. They hand the paper bag to the sergeant, right? And he was instructed never look in the bag, right? So the sergeant, he'd hand it to the sergeant. Every time he brought it over, the sergeant would smack him. Did you look in the bag? Right? He'd say, no, I don't. He gets smacked anyway. But at any rate, so the reason why I brought it up is because he had a million expressions from those days. One of the expressions, if like somebody disappeared, like Vinny's no more, right? They would say Vinny took a cab. Right, so when you say you had to take a cab, it brings up the memories that they wouldn't say that Vinny's like gone, Vinny's sleeping with the fishes. They would say Vinny took a cab. Take care. Have a good.
I think he's trying to say something. I don't know.
Okay, so at any rate, he had a million stories. Let me tell you. Okay, so duct like standard airflow is galvanized iron duct. How are we doing on time?
Doing well.
We have.
What do you mean well? Okay, we're more than halfway through. Okay, so standard airflows. Let me see how many of these slides I have left, because I may want to. Oh, we're going to go through this pretty quickly now. Okay.
Take a break.
Yeah, let's take a break. Let's take a 5-minute break.
Yes.
Okay, good. Good idea. And when we come back, when we come back, we're actually going to do an exercise. We're going to do a lot of these calculations. In fact, I may ditch the rest of this and go right to the exercise. Yeah, we can go straight to that exercise. I think that makes sense.
No, the A and C.
Because we're going to be doing this anyway.
I don't know.
Oh, there's a good picture of that, the R over D. I should make sure I cover that. I'll do the exercise first.
Oh, so when will we have the results of the test so we can know into
Test? The exam, the homework you mean?
the homework? Sorry.
I'll grade them like in the next day or two, and then you can redo it.
Okay.
It's more of an assignment than a test. We have a test in
Yes.
it. You have a midterm and a final in this course. The midterm's probably going to be all on exhaust duct, and the final will probably be indoor air quality. So we'll break up those two. When we get into indoor air quality, we're going to really shift gears because we're going to start talking about the dilution ventilation instead of exhaust ventilation. Kind of a different animal. So after the midterm, all of a sudden we're going to get into this new.
Hello, sorry to interrupt. Does anyone have a gray SUV or blue Honda in the garage?
I have a blue Hyundai. GB something.
They didn't. They just said blue Honda. They said they were about to lock up the garage. So hurry.
Oh, usually they let me out. Nelson
But
let me out.
that's who called.
They called?
Yeah, I just got the call. I don't know what's going on.
All right, well, let me go down. So I'll tell you what, we're on a break, so let me go down and take care of this.
Take your time.
Don't
worry.
Actually, I should take my coat. Actually, my cue.
Don't take a cab.
Yeah, take a tip. Maybe the building guys are not around tonight. Is there a parking lot around here besides this? Hey, Stavros, is there a parking lot around here?
Parking lot?
Yeah.
I'm not sure.
But I saw a guy park across the street
Maybe
yesterday.
they'll get lucky.
Yeah. One of our classmates parked across the street.
Yeah, I could take him the whole rest of the period to find a parking spot. I could take him the whole rest of the period to find a parking spot.
I know.
And the rest of
It was funny that this is at a museum, a children's museum.
What museum?
Children's museum.
Children's museum?
Yeah.
Oh, okay.
Nice.
Oh, it's being recorded still.
I can see the game.
Wow, she's really good at that.
Actually, 21 months.
Wow.
Yeah. I should see yourself in the. Thank you.
Okay, no, I'm safe. Now, there's somebody down there that didn't pay, right? So they close the register and lock it up. The building guy can let me out, but I have to, like if they didn't pay, he won't let you out. Okay, but we all here. It was missing a couple of people still.
Really?
What did you try? It's still fun. A lot of don't do it if you have that really
Fun stuff.
you don't do fun stuff. Yeah, you like it.
Okay.
That's good. Which one?
How was it good?
That's it. I got extras of these if you mess up. Do it again.
Oh, thank you.
Okay. So I'm going to give you a situation. You are called in by Tiffany's. I've seen setups like this. They have a jeweler whose job it is to do the final finish on precious metal rings and stuff like that. Okay. Now this guy's job is to grind off any like rough spots and then use like a couple of wheels that are in his table to polish it down. He might use like an abrasive material, maybe like aluminum oxide in a water solution that he shakes up and puts on the wheel, and he spins it around. Some of the dust comes up, and a rouge wheel next to it, which is dry, has a red rouge powder on it that he uses to do the final polishing. So he does some grinding with a kind of a Dremel type device. He does some polishing with an abrasive material, and he does some polishing with a very dusty rouge material. So basically, he's producing particulates, and we want to keep those particulates out of his breathing zone. His table is roughly 2 feet deep by 6 feet long, and he's got this equipment in it. So we want to find a hood that's appropriate for a minor grinding operation that's going to be built into this kind of thing. So what are we going to do? We're going to go to our catalog of hoods, right? Our catalog, your real catalog of hoods might be, you would go to a manufacturer's catalog and stuff like that. Our catalog of hoods are typical hoods that you might find in industrial environments that basically are kind of generic versions of what you might get from a particular manufacturer. So we need something for a grinding operation. But this slot hood looks pretty good, but let me keep going through here. Hood grinding hood table. Look at that. It's even got a couple of polishing wheels in it and stuff like that. That looks like something that meets our application. Okay, so what do I need to know about this thing? First thing I need to know is, how am I going to figure out what my capture velocity has to be and how much air that I have to move? Okay, well, let's see. I got a couple of formulas here. This formula here, Q, what is that equal to? It's equal to, let's see, transport velocity, you want 3,500 feet per minute. It's transport velocity for dust. Remember we said 3,000 to 5,000. It's kind of light dust. So the number of cubic feet per minute is, for this particular hood, is going to be 250 times the area of the table squared. Is that right? AT? You don't always design these factors. Area of the table, I would say that probably means. So what's the area of the table? What I say, 2 feet by 6 feet by I don't remember what I said. 6 by 2. So that's 12. 12 times 250 is how much? 12 times 250.
3,000.
Okay, 3,000. So we want. So we want our Q is going to be equal to 3,000 cubic feet per minute, right? That's Q. So we're going to take a look at this thing now, and okay, what's our K factor for this hood? I remember it. Do you guys remember it? 0.5, right? It was 0.5. 0.5. I'm going to change the Q a little bit. I'm going to say it's 2 feet by 5 feet. That's kind of a big table. So that's 10 times 250 is going to be 2,500. Q's are going to be equal to 2,500. So now I need to figure the table is 2 feet by 10 feet. right? And Q is equal to 10, excuse me, 5, is equal to 10 feet squared times 250, right? Or 2,500 cubic feet per minute, right? That's our 2,500, our Q. Okay, so now I want to figure out what my static head pressure has to be in order to give me that much air. So I mentioned that this is a 12-inch diameter duct at the back of this table, right? What velocity do I need in this 12-inch diameter duct in order to achieve 2,500 feet per minute? Well, Q is equal to V times A. So the velocity is going to be equal to Q divided by the area of the ductwork. So this is 12 feet, 12 inches in diameter, right? So I'm going to say to myself, okay, what's the area of a 12-inch diameter duct? So I'm going to go over here. I think it's 0.866, but I'm going to calculate it anyway. 0.866. I'm going to actually calculate 3.14. Whoops. 3.14 times the radius squared. Radius is half a foot times 0.5 times 0.5 is equal to 0.785. That's our area, cross-sectional area, right? So our velocity is going to be equal to 2,500 divided by 0.785, right? 0.785 is in square feet. 2,500 is in cubic feet per minute, so it's going to come out to be feet per minute. So I'm going to put that into my memory plus, clear that, and 2,500 divided by that. So the velocity is 3,184. I'm going to call it 3,185. So V is equal to 3,185. What are the units? Feet per minute, right? 3,185. So now I need to know what my velocity pressure is going to be. What's my velocity pressure going to be here? And bingo, chart, exactly. So chart 7, what was it again? 3185. 3185 is going to be about 0.63. Everybody in agreement with me so far? Equals 0.63. Okay. Now I have to figure out what's my static pressure going to be at that point, right? Well, how do I figure out what my static pressure I need to generate this amount of velocity pressure? I have to figure out my head entry loss, my hood entry loss. My hood entry loss is equal to the velocity pressure times K times D, right? D I'm going to ignore for our purposes. So it's equal to 0.63 times, what was K for this hood? 0.5 is going to be equal to 0.3. I'm going to call it 0.31. So our loss is going to be 0.31. That's our head entry loss. So what's the total static head pressure have to be? Total static head pressure, the hood, is going to be equal to the velocity pressure plus the positive value of the static pressure of the head loss. Right? It's going to be 0.63 plus 0.31 is going to be 0.94. So our static pressure hood is going to be equal to negative 0.94 inches. Everybody in agreement on that? Okay, not complicated, right? What I'm going to do down here is I'm going to chart the loss of energy as we go through this ductwork. Okay, here's 0. So 0.84 is going to be roughly around here.
Units, can you use units?
Inches of water. Right? There's always inches of water.
If we choose from the chart, does it give us the velocity pressure? We can choose a different unit.
You can, yes.
If we do,
There's a chart 5A and a chart 5B. 5A is English unit, American units. 5B is all metric units.
So if we do that, then the next calculation for the head entry loss and the static
all going to be in inches.
They all change?
They're all, no, they're going to be the same, but they're going to be in the new units.
Oh, yeah.
They're going to be different, but it's going to be the same. It's going to be physically the same pressure, but it's going to be in new units. Right?
Yes.
Make sense? Okay, good. So what happens next? Now we go 100 feet with this 12-inch diameter duct, right? Galvanized duct. And we want to know how much pressure do we lose going through that ductwork. So how do we calculate that again? That's going to be equal to, okay, let me see if I can make some room for myself here. I'm going to pull this out. Okay, so that's going to be equal to, right? The static pressure the static pressure loss, right, is going to be equal to, it's going to be equal to the K factor for the pipe for the duct times the length of the duct times D. So we have to look up this K factor for the duct. That's 12-inch diameter galvanized iron duct. Okay, so 12-inch diameter. Oh, hang on a second here. Times the length times the velocity. K times the velocity pressure times the length. Right? Because we got to, we still need to find the actual pressure loss. Okay, so let's go to our chart 5. I'll do it from there. Okay, so I'm going to put annotate this with a arrow. So let's see, 12-inch diameter duct. And the velocity is how much did I say it was? 30, anybody remember?
3185.
31, say 3,200, right? Is going to be about there. And it was 0.63, so this looks about right. Right, the velocity pressure was about 0.63. So what's the loss per foot of ductwork? It looks like it's 0.016, let's say, 0.016. I'm going to call it 0.016. So what's our loss here? Our static pressure loss is going to be equal to 0.016 times the velocity pressure. What was that again? 0.63.
It wasn't 0.31?
No, that was the loss, the hood entry loss, right?
The H. That was the H.
That was the H, the hood entry loss, right? The velocity pressure was 0.63. That was based on the velocity. Okay, times the length. How much is the length? 100 feet. Right? Times D, we're going to say D is equal to 1. So let's calculate this. How much of a loss do we have here? Okay, clear? Clear. So it's going to be equal to 0.016 times 0.63 times 100. So how much static pressure do we lose? We lose 1 inch. So 1.01. I'm just going to say 1 inch. So it goes from what it was before, which was 0.8, what was it again? 0.81, down to negative 1.81.
Wait, no.
0.94. Did I make a mistake there?
0.945.
0.945? Okay. So 0.945, it goes from 0.81, add point, now we have to replace that. Huh?
No, sorry, at the beginning it was 0.94.
Was it?
Yes.
Oh, you're right. You're right. This is 0.94. So now this is negative 1.94. So why did I do that? I have to, in order to have a suction pressure, in order to have a suction pressure of 0.94 here, I have to make up for the pressure I'm going to lose through that ductwork. So this has to be a negative 1 inch water higher suction pressure here, because I'm going to lose that getting back to that point.
Oh, so you added 2.
Yes.
Okay.
Okay, I added 2 because if this were 0.94, it would be 0 back there, practically.
Okay.
Right? So I need to make this a bigger static pressure, a higher suction to make up for the loss of suction getting pulled through that pipe. Okay, so now what do I got? Now I have 2 elbows. Okay, now I'm going to make, why do we have an elbow here? Maybe there's a pole here. Got to go around the pole. Right.
I'm lost.
Yeah, let's do the last
Let's
step
do
again.
the A again. I'm lost.
Okay, over here. we calculated that the static head pressure is equal to the velocity pressure plus the hood entry loss, right? The velocity pressure turned out to be 0.63. We got that from changing velocity. Okay, the head entry loss, the amount of suction that we lose getting to that point, is equal to the velocity pressure times the K factor for the hood. That was 0.63 times 0.5. So it came out to be 0.31. So 0.63 is the velocity pressure. 0.31 is the loss in the static pressure that we achieve, that we run into going through here. So in order to make the velocity pressure 0.63 here, we have to add 0.31 to make up for that loss. So the static hood pressure here has to be negative 0.94 in order for us to achieve that velocity. Okay? And we need that velocity because that's what we need to capture the contaminant. Okay, we're all on the same page now, right? So now the next problem we have is that we're going to lose static pressure to this ductwork, this ductwork we have to go through, the 100 feet of ductwork. How much static pressure do we have to make up for that's going to be lost going through that ductwork? Well, that's equal to, let me bring this back here. Yeah, that's equal to 1 inch. And how did we get that? We got that by saying the static pressure is equal to the K for that particular kind of pipe times the velocity pressure times the length of the pipe. Well, for galvanized iron pipe, it's 0.016. K times VP is that's 0.016, right? We looked that up on chart 5, right? Because it depends on the velocity and the kind of duct size, right? 0.016. The velocity pressure is 0.63. So that turns out to be 0.91, right? Am I right? Something like that.
Times 100.
Right. Right. Times 100 feet. Times 100 turns out to be 0.9.
I think it's
No,
1.1.
1.1.
Yeah.
Is it 1.1?
1 point something.
Should I do it again?
No, it's 0.1008, right?
Oh, yeah. Yeah, there you go. Yeah, there it is right there. Okay. So that's basically 1 inch. So I lose 1 inch. So now the suction pressure before, we need, in order for this hood to work, we need negative 0.94 inches of static pressure there, right? And in order to have that there, we have to have another inch of static pressure at this point because we're going to lose it to that length of ductwork. So we have to make up for that loss. Now we got 2 elbows here. We got to make up for that loss as well. What do we have here? 90-degree 5-section galvanized iron elbows. I didn't say the rate. Let's assume the radius is 1 to 1. Radius and diameter is 1 to 1.
Can we just stop there?
Yes.
So I understand that at the point A, then the static pressure is going to be minus 1.94, is that right?
Yes.
Because we have to make up. Right.
Yes.
Thank you.
Point A, yes. Okay. I forgot to put letters on.
Yeah.
Yeah, there you are. Right there you are right there. So in fact, I can demonstrate this. This is actually, you could actually, this is actually a linear loss. You're going to draw a straight line between, a kind of a straight line, right? That's kind of a straight, let me undo that. You could draw a straight line between, I can't do it with this graphics tab. You can draw kind of a straight line between those two. If you had a ruler, to do it with. I'm sure there is, but for me to find it now, yeah. Yeah, that's exactly what I'm gonna do. I'm gonna grab one of these lines up here. I gotta turn that over.
Oh, you do?
I don't know.
What happened?
Oh, okay, thank you.
No,
I guess it makes sense. It makes sense that
Yeah.
what's it? Wait, you
Yeah,
multiply.
yeah. That's what was happening.
So then,
Okay, I'm gonna wait for everybody to get settled with this.
Right.
Okay, so now we have more resistance. We're gonna lose energy to 2 turns. There were turns, a lot of times you're going to run into turns in ductwork because you're working in a plant, there are going to be obstructions. You got to go around lighting, you got to go around posts, support posts and stuff like that. So in this case, I'm going to say it's 2 quick turns. I'm going to ignore that length of ductwork in between. I'm just going to say it's 2 90-degree turns. Okay, 5-section galvanized iron, 2 90-degree turns. Let's figure out how much of a loss that we're going to get there. But what's the velocity pressure here? No, velocity pressure. 0.63. It's always going to be the same as long as we don't change the diameter of the ductwork. The velocity is always going to be the same.
I'm actually following, so that's you.
Okay, good. So, I left this out, but I'm going to call this the radius and diameter is going to be 1-to-1. So it's going to be a 1-foot diameter churn and 1-foot diameter duct. So I'll call it 1-to-1. So let's look up what the K value is for that duct. Okay, for that shaped duct. And that's going to be table number, elbow losses, number 13. Okay, so it's 5-section. Here's a 5-piece galvanized iron, radius 1-to-1. So the loss is going to be, the K factor is going to be 0.33, right? So what's my loss going to be there? My loss for each one of those elbows is going to be equal to my velocity pressure, the elbow loss. Oops, I got to click this again. My elbow loss, my elbow loss is going to be equal to 0.33 K. It's going to be equal to K times the velocity pressure times the density factor. 0.33 times, what was this again? 0.63. Okay, what's that going to be equal to? It's going to be equal to 0.33 times 0.63 is roughly about 0.21, right?
Times 2.
Exactly. Times, now we're going to multiply it. There's 2 elbows. So we're going to multiply that, so it's going to be 0.42. So now, in order to achieve, let me pull this back over. Now, in order to achieve 1.9 suction pressure at point A, which will achieve 0.94 suction pressure at the hood entry, in order to achieve that, now this has to be a greater suction pressure. And how much greater? What do we just calculate? 0.42 inches, right? So what's that going to be at that point? Is going to be 0.42 on top of what it was at A, which was, I think, I'm going to call it 1.9 plus 1. Is going to be equal to negative 1.9, 4.2, 1.32, 2.32, right? Negative 2.32, maybe about here. Okay, yeah, whatever. Okay, so that's the pressure's gone down again now, right? We have to have more suction because we're losing energy to these transitions. Okay, so now what do I have next? Now I have 10 feet of galvanized iron ductwork. Didn't we just look up the K for that? What was the K factor for that? K factor for that was 0.16, right? So the static pressure loss to that is going to be 0.16 times 0.63 the velocity pressure times the length of the ductwork, which is in this case only 10 feet. Oh, actually, the K factor was 0.016. 0.016. 0.016.
No,
0.016. So clear 0.016, the K factor from our table, times 0.63, times only 10 feet this time. So the loss on that 10 feet is only 1/10 of an inch of water. So that's going to go from 2.4, I guess it was, to 2.5, negative 2.5. Right? That's for that length of ductwork. Okay, now we got a curveball. The fan opening here is 18-inch diameter. So I have to size up the ductwork to fit that fan. So I need to put a transition in here. I have to go from 12-inch duct to 18-inch duct. And I do that with a gradual transition piece. That's an expansion, right? I'm going to show you a couple of rules for expansions and contractions. Okay, let me find it here. Okay, I want to blow this up. Okay, if you're doing a contraction, right? Doing a contraction, you're going from a big duct to a small duct. What's going to happen to the velocity pressure? It's going to speed up. It's going to speed up. Velocity pressure is going to go up, right? Static pressure also is going to change, but velocity pressure is going to go up. For a contraction, you got two static pressures. You have the beginning static pressure in the big duct, and then the finished static pressure in the small duct. Static pressure 1, static pressure 2. For contraction, static pressure 2, right, where you finish up, is equal to static pressure 1, the big duct, static pressure, minus the velocity, the change in the velocity pressure. It went from a small velocity pressure to a higher velocity pressure, right? It went up. Times minus the change in the velocity pressure. That's minus the static pressure loss. Okay, we're going to look at a factor to figure that out. Okay, now for expansions, the static pressure, the second part is equal to static pressure in the first plus the velocity pressure change minus the static pressure loss. Right? Okay, so now let's take a look. So we have a chart here for static pressure loss for contractions. Expansions and contractions. Here we go. Okay, so for tapered contractions, this is what it looks like. For expansions, this is what it looks like. So one of the things we're interested in is the relative diameter of the two ducts. I'm going from a 12-inch diameter to an 18-inch diameter. So what's the relative diameter? It's 12 divided by 18, it's 2/3, right? So I'm going to say roughly 0.6. Now, you also then have to say how fast the taper it is. I'm going to say it's a 15 degree. Did I say it on there? If I didn't say what? Yeah, 0.7. Yeah, wise guy. There's always a wise guy in the crowd. You're right. As it happens, this time you're right. So it's 0.7, right? It's closer to 0.66, right? 0.7. I'm going to call it, I don't know if I told you the taper angle, but I'm going to call it 15 degrees. So the K factor is 0.23. Okay.
Wait, what's that?
The K 15 degrees. That's like the angle of the duct here. They probably show. See this little theta here? That's the 15 degrees. In other words, if it goes like that, that's a big angle. It goes like this, it's a small angle. Okay. The more gradually angled, the smaller the K factor is. Right? You're going to see that if the taper angle is lower, it's going to be less. 0 degrees is basically no taper at all. Right? So at any rate, so that, what did I say it's going to be? It's going to be 0.23. That's my K factor. Now, what do I multiply my K factor by in order to determine the static pressure loss? You multiply it not by the first velocity or the second velocity. You multiply it by the difference in the two velocities. Okay? What's the difference in the two velocities? Well, we got to calculate that. What's the difference in the two velocity pressures? Okay, what's the velocity pressure in the let me find this again. Okay, what were we, no, velocity pressure, not static pressure, right? It was at 0.63, right? The velocity pressure is 0.63, right? 0.63. What's the velocity pressure in the 18-inch duct? Well, now we have to calculate that, right? Q is equal to VA, right? So what is Q equal to?
V stay the same, so.
No.
V.
Well, the velocity is going to change, right? Now Q stays the same. What was Q? Q is 2,500, right? Now the area, instead of being what it was before, the area now is 1.5 foot or 3/4 foot radius. Okay, let's calculate that. Now this is pretty interesting stuff, right? I mean, you're really what we're doing here is designing a ductwork system. Okay, so where was I now? 2,500. Wait a second. I got to find the area first. The area is going to be 3.14 times 0.75 times 0.75, right? Pi r squared, radius squared. So the area is 1.76 square feet. I'm going to call it 1.8, right? 1.8 square feet. So I'm going to put this into memory. Okay, so now I'm going to take my 2,500 cubic feet per minute, divide it by the new area, and it's going to be equal to now 1,415 feet per minute.
Oh, that's yeah.
Right, okay? So what's the velocity pressure now? Anybody want to hazard a guess on what the velocity pressure is now?
The chart.
Well, the velocity pressure, right, go to the chart, okay? Chart 7, I guess it was. I forget which one it is now. Wrong chart. Don't need this one anymore. Velocity, okay, well, and what was the number I just gave you? 37. I hate this. I'm shot. I'm telling you, get to a certain age, you can't remember shit. 1415. 1415. Okay, 1415. Okay, I'm going to say I'm going to call it point. You tell me which one's closer now, since you're going to give me a hard time about it. 1415, about in the middle, right? Lower? No, higher. 0.13. I'm going to call it 0.13. I'm going to put the chart away quick so you don't see it. 0.13 is now the velocity pressure. 0.13 is now the velocity pressure. So now what's the difference in the velocity pressure? The difference in the velocity pressure is now 0.5 inches. I multiply that by my K factor. My K factor was what? 0.23 times 0.23, right? Right from the tapered duct, that was 0.23 at that 15-degree taper. And that's going to be equal to 0.23 times 0.5 is about 0.13, let's call it. 0.13. 0.13 is going to be my static pressure loss, is 0.13. So now, let me go back to my equation. Okay, static pressure 2 is going to be equal to static pressure 1, which was what, 2.5 or something like that, plus the velocity pressure change minus the static pressure loss, right? So it's going to be 2.5 minus the velocity pressure loss change plus the velocity pressure loss, 2.5 minus 2.5 plus, what was the change? The change was 0.13, right? No, it wasn't.
0.5.
0.5, you were right, it was 0.5. The difference between it was 0.63 minus 0.63 minus 0.1 is 0.5. So it's minus 2.5 plus what did I just say? 0.5, which is 1.9 minus the static pressure loss, which was the static pressure loss again? It's up here, which was 0.13. So 1.9 minus 1.9 minus 1.3 is minus 2.3. So it's going to be minus 2.3. Okay. So now, okay. Minus 2.3. Okay. So now what happened here? Something weird happened here. The static pressure could actually be lower now to achieve what we need. But that makes sense because it's slower movement and it's a bigger duct, right? It kind of makes sense that it would go up now. Going from a big duct to a small, I should have really done one where it went from a big duct to a small duct first because that's more intuitive, right? But if you stick with the formulas, it should work out okay. So to finish up, I want to finish this up now. Now we got 10 feet of galvanized iron duct, 18-inch diameter. I got to figure out the K factor for that. 10 feet. I'm just going to say that it adds another tenth, and I'm going to go over here. So we come to a filter. Now the filter, the manufacturer may tell you that's going to introduce a 0.3, a half-inch loss. Actually, it could be more than that. Say a 1-inch loss across this filter, right? So that loss across this filter now may bring us from a negative 2.3 to negative 3.3. And then we have another length of linear 18-inch ductwork. We're going to have a little bit more loss, negative 3.3 to negative 3.5, let's say. That brings us to our fan. So what do I know now? I know Q, how much air I have to move. I know the velocity. I know the static pressure I need to generate at this point. If I know Q, I know how many pounds of air per minute I need to move. And I know what kind of suction pressure I have to generate there. I can figure out how much work that is. I know how to design. I can now know how to design this fan for it, the correct horsepower, for the correct velocity of air, for this suction pressure. Now that I know what the suction pressure has to be there to achieve what I need at the hood, I can design the rest of this system. That's what this is all about, right? Now, we left one important part about this is that it's not just discharging to free air here. Now, there's more ductwork going outside. We'll start to add that on afterwards once we get this down pretty solid. Okay, so what have you done? You've designed 80%. The other part's like 20, a little bit more, say 30%. 20% is figuring out what fan you need. The other 10% is the exhaust. You've done 70% or more of the design of a system for a jeweler that's working at Tiffany's. Right? Pretty impressive, right? And pretty cool, and not something that's unapproachable. Why is it not unapproachable? Because we've been given tools to be able to do it easily. Now, next week, we're going to do this again after we do some other cleanup stuff and look at some other stuff. Because now we got to worry about, well, what if you want to have another duct you want to tie into there? So there's going to be conjunctions, joining of ductwork and stuff. So that's going to get more complicated. We'll just introduce that next week. But what we should do is do another one of these examples, except we're going to do it using a prepared spreadsheet. So that all we have to do is plug the numbers in and it'll do the calculations for us. Yes?
Well, next time we do have this kind of exercise, if you give us a few minutes to work like a group working. So
yes.
First,
okay, I'll tell you what. Next time, I'll post this online so you can look at it before you come here. But would you rather do it here?
We do it here, but then
okay. I will give you a similar example to this. Give you a hood I'll give you the situation. You have to pick out the hood, and I'll give you the layout that will, like the layout, the sizes and so on and so forth.